All right. Okay. Well, we will continue on in our lectures on NumPy or NumPy. So we introduced this on Friday. We said NumPy brings a new data structure to Python. It is the NumPy array, okay? The array. And what's important is that all of the values within an array are of the same data type. So, most commonly, you will have arrays of floating point numbers. But, you can also have arrays of logical values or Boolean values, true, false values, arrays of integers and things like that. But the key is that every single value in there is going to be of the same data type, as opposed to a list where a list can contain different data types. You can have strings mixed in with floats, mixed in with integers and things like that. But the NumPy array, everything's of the same data type. That allows for the computation and doing math operations with NumPy to be very, very, very fast. Which is going to be important, especially when you're dealing with kind of large data sets and things like that. So we looked at that. We said, in NumPy you can have one-dimensional arrays. One-dimensional arrays just have a length. And then you can also have, multi-dimensional arrays. So you can have two-dimensional, three-dimensional, higher dimensional arrays as well. There's an important distinction between a one-dimensional array and a two-dimensional array with one row or one column, okay? So a one-dimensional array of length 12 is very different from a two-dimensional array that's one row, 12 values, 12 columns, okay? All right, so anyway, let's go ahead and take a look, and we're going to look at some additional kind of things that you can do with arrays. So as always, we will import NumPy, okay, and we'll import NumPy as NP. Let me start this up, okay. All right, so one of the operations you can do is to concatenate arrays. You can just take two arrays and just join them together, okay? So here I've got X, I've got Y. Both X and Y are one-dimensional. Okay, so when I print out X, it's 0, 1, 2, 3. When I print out Y, it's 100, 101, 102, 103. And then if I concatenate them, it just joins them together. Now there's only one axis along which I can join them because these are one-dimensional arrays. So it's just kind of like taking a line, tacking on another line, and then now you have an array that's length 8 with the values that you have in there, okay? Concatenate allows for an axis argument, okay? Now in this case, it's redundant because there's only one axis, okay? Axis 0, the 0 indexed axis. And so here I can say, concatenate, arrays X and Y along axis 0, and we get the exact same result, okay? Now, if I tried to say, hey, concatenate along axis 1, okay, we get an error. It says axis 1 is out of bounds for an array of dimension 1. So it's saying, basically we're saying concatenate the array along the second dimension, but these are one-dimensional arrays, right? So they only have a length. There's no kind of width. There's no rows or columns. It's just a length. And so I'm saying, hey, try to, it's like if I give you two line segments and I say stack them on top of each other. Don't put them end to end, but I say stack them on top of each other, and it feels confusing because you're like, how do I stack a line on top of a line? And that's basically the same error that Python is throwing here. NumPy says you can't do that. Okay, and again, if you check the shape of either thing, okay, then it will say it's one-dimensional. Okay, length 4, that's the shape. Okay, now there is something called VStack. Okay, VStack says, you know what? We will take these one-dimensional arrays and I will stack them vertically. And basically, VStack will give that one-dimensional array a second dimension, and it will change it from a length 4 one-dimensional array into a 1x4 two-dimensional array, and it will do it to both x and y, and it will stack them vertically. So now we will have a 2x4 type of thing, okay? So that's VStack, okay? And then there's the corresponding HStack, which will stack them horizontally, okay, or extend them horizontally. Another way you can do something like VStack without specifically calling VStack is you can reshape them into 1x4s, okay? And so now you can see this is a two-dimensional array. Reshape y into a two-dimensional array, which is 1x4, and then you will concatenate them, okay? Now, if you concatenate x and y along axis 0, okay, axis 0 is now the number, it's, when you talk about a two-dimensional arrays, axis 0 is the number of rows, and axis 1 is the number of columns, right? You go rows by columns. So axis 0 is rows, axis 1 would be columns. So here, if we stack along axis 0, okay, basically, you know, our shapes are 1x4 and 1x4, and we're saying stack them or concatenate the axis 0. So we're going to do 1 plus 1, and we get 2, and so now we get a 2x4. Okay. So index 0, axis 0 is for rows, and axis 1 is for columns. So here, if I say concatenate, you know, the 1x4 array x and the 1x4 array y after we reshape them along axis 1, okay, then we will get a 1x8. Okay, and so this is two-dimensional, is 1x8. Okay. Similarly, you know, if you have two-dimensional arrays, okay, so I have x and y, xm and ym. Xm is 2x3, ym is 2x3. If I say what's the shape, xm and ym are both 2x3. And so if I say concatenate and I don't provide an axis argument, the default is going to be to use axis 0. So what will the result be? So if I say and concatenate xm and ym, what do you think? Will I get a 4x3 or will I get a 2x6? We'll get a 4x3, okay? Because we're doing axis 0. Axis 0 is the two rows and 2 rows. We're adding those together, okay? So we're going to get 4 rows, 3 columns, okay? When you say concatenate, okay, if I specify axis 0, I get the exact same thing. Okay, and if I say axis 1, okay, axis 1, again, I've got a 2x3 and a 2x3. We're going to be adding the 3 and the 3, so then we'll get a 2x6. So here, if I concatenate along axis 1, we get the 2x6, okay? So just make sure you understand how concatenate works. It's I think a fairly, it's not the most commonly used operation, but it's, I would say it's common enough where, you know, if you have a matrix and you have a matrix, a lot of times you kind of want to just join them up, right? And so if you want to kind of extend the number of columns, you'll do it along axis 1. If you want to extend the number of rows, you'll do it along axis 0, okay? VStack and HStack do kind of what you expect. So VStack will stack them vertically, so you'll get a 4x3. HStack will stack them horizontally, so you'll get a 2x6, okay? So I would say, you know, for me, I generally use concatenate with the axis argument, but VStack and HStack exist, and you might see them in other people's code as well. Okay, I guess the reason why, so, because like for me, concatenate, I can predict very well like how it's going to work because I'm specifying the axis. I don't know, like if I have a 3-dimensional array. Okay, I didn't set up arguments, but like if I do a 3-dimensional array and I say along axis 0, I just know that like I'm going to be adding, you know, the dimensions of axis 0 together, and I know exactly what I got. But actually, if I have a 3-dimensional array, I don't know, like can I do H stack or V stack? And I'm not entirely sure. I don't know how a V stack or H stack would work with a three-dimensional array. I'll have to try it out. But I just, okay, well, anyway. All right, so here we can do math operators with NumPy arrays, and they are, I guess, what we would consider vectorized. Okay, so if I take x, which is 0, 1, 2, 3, and I say plus 5, that plus 5 is going to get what we call broadcast or repeated across all the values 0, 1, 2, 3. So we get 5, 6, 7, and 8. Okay, if I do x plus y, they're vectorized, so you get element y's addition. So it's going to do the 0 plus 100, the 1 plus 101, the 2 plus the 102, and the 3 plus the 103. It's going to do first with the first, second with second. It lines them up. Same thing when you do star multiplication. Okay, star multiplication. This is element-wise multiplication. So it takes the first element, multiplies it with the first element, second element, multiplies with the second element, so on and so forth. So you get 0 times 100, 1 times 101, 2 times 102, 3 times 103, and you get 0, 101, 204, 309. Okay. You can multiply them together and then sum them up. And that's basically a vector dot product, right? So if you think about, vector A and vector B, and you say do the dot product between them, you're basically multiplying the elements element-wise and then adding them together. And so if you have a vector 0, 1, 2, 3, and 100, 101, 102, 103, and you say do the dot product, you'll get 614. There is a NumPy operator called numpy.dot. Okay, numpy.dot will do the dot product as well. So numpy.dot.xy will also give you the value 614. Okay, this is just the number 614. This is wrapped in this thing that says np.int64. This is technically, it's just telling you the data types, the integer, 64-bit integer 614. Okay. You also have matrix multiplication, so it's kind of like doing vector x matrix multiply vector y, which is effectively also the dot product in this case, and so you also get the same result, 614. Okay, but the @ sign is for matrix multiplication, and that will generalize to say like a two-dimensional matrices, right? So you could do matrix x with n rows and k columns, multiplied by matrix y with k rows and j columns, and the result will be n by j or something like that. So that will be the @ sign. The @ sign is the matrix multiplication operator. So just make sure you understand. I think we're accustomed to this if you've been dealing with computer programming and stuff. So like in R, you also have the star operator, which does element-wise multiplication, and then you have the in R, the matrix multiply operator is the %, % operator. Python uses the @ sign. Okay, all right. So again, xm and ym are these 2 by 3 matrices or arrays. So you have xm is 2 by 3, ym is 2 by 3. Again, if you do a plus 5 plus a constant, it just gets broadcast across the whole array. So 0, 1, 2, 3, 4, 5, you get plus 5. Element-wise addition, the plus sign does element-wise addition. So it 2 by 3 plus a 2 by 3 gives you a 2 by 3. Okay. The star operator. Okay. So in linear algebra, we do not have the equivalent of this operator, I don't think, right? Is there something where you can take a 2 by 3? I don't think there is, right? In classic linear algebra, there's nothing, right? There's a 2 by 3 matrix and a 2 by 3 matrix. You can't do these things and you get a resulting 2 by 3 matrix, okay? But we do it all the time in computer land, okay? So I don't know, whatever we call this, right? This is just the element-wise multiplication operator, and we just do, the 2 by 3, you just multiply the top left corner by the top left corner, and the next element by the next element, and the next element by the next element, and you get exactly what we expected. We just, like in linear algebra, there isn't an operator like this. So when you see going from like papers written on this. People just make up new symbols to have this operator. But I mean, it's common enough, and I think it's, mostly well understood enough, okay? The same thing, you have np.multiply, okay? So this is the same thing as the star operator, okay? xm, ym, why would we want to use this or something? There's additional arguments you could do with multiply, like ignore missing values and stuff like that, things like that. Okay, well anyway, all right. Okay, here's xm and ym again. All right, so if you wanted to do like linear algebra type multiplication, you would have to transpose y, because if you want to do a 2 by 3, you have to multiply it by something with 3 rows. So we could transpose y, so we get 3 by 2, and then we can call np.dot, okay? np.dot will basically do the matrix multiplication operator. The 2 by 3 times the 3 by 2 will result in a 2 by 2, okay? You can also do xm dot, okay? xm dot, so you can take the matrix itself, xm dot, and then you provide the matrix that you want to multiply it with, ym transpose, okay? And that gives you the same result. Or this is probably the preferred thing is xm and then the matrix multiply operator, the @ sign, ym transpose. And this is probably, this one I think feels the most familiar in terms of going from math notation into computer notation. And that's what we have, okay? But this wasn't implemented until a little bit later in like the NumPy life cycle. So like we use it all the time now, but like if you look at code that used like old versions of NumPy, this operator didn't exist, and so you'd see this, dot business, okay? But that's what we have, okay. All right, here's again, I have an array 0, 1, 2, 3, okay, one-dimensional array. Basic math operations, +4 adds 4 across the thing, -5 times 2, divide by 2. Okay, so notice all of these are integers. When I do the divide by 2, everything's going to become a float, right? And you can see that because it has little decimals, right? So x times 2, integer times integer, results in an array with integers, 0, 2, 4, 6, all integers. And here, now that I have floats, we get 0, 0.5, 1, 1.5, okay? If you put a minus sign in front of everything, then it makes everything minus. The power operator, ** gives us that. You have modulo division, you have the absolute value. All right, so this is all just kind of basic math. I think none of this surprises us, okay? NumPy has trig functions, so you can, I think in your first homework assignment, you had to import module math, okay, and then you would have functions like sign, and it would be like math.sign. NumPy also has its own kind of math operators, and I would generally recommend, if you're going to be working with an array, then use the NumPy functions. Okay, so the NumPy functions, I mean, a lot of them work identically, the math function and the NumPy equivalent function. So like math.sign and NumPy.sign, I think, well, I don't know. I don't know if they work identically, but a lot of times, a lot of these things, some of them work identically. Other things have, like the NumPy ones, have been optimized for NumPy arrays and things like that. So in general, I would recommend using the NumPy version of these functions. Okay. So anyway, we have. I'm going to create a vector theta or an array theta. I'm going to linearly space from 0 to pi. I want 5 of these, so I'm going to get 0, pi quarters, pi halves, 3/4 pi, and pi. Okay. Right. So this is pi over 4, pi half, 3/4 pi, and pi, okay? And then I could say, all right, what is sine of this thing? NumPy dot sine, right? And so we get 0. Okay, yeah, 0. Sorry, my eyes are playing tricks on me. Okay, 0, and then this is root 2 over 2, 1, root 2 over 2, and then basically 0. Okay, this is 1 times 10 to the minus 16, and it's just, this is the limits of our floating point math, but basically 0. Okay, with cosine, you know, you get 1, and then root 2 over 2, then basically 0 at 6 times 10 to the minus 17, and then root 2 over 2, and then negative 1. And then tangent, this is where we get, so we get 0, then 1, and then this is 10 to the 16, which is kind of like approaching, but not, you know, getting towards infinity, okay? But again, floating point, right, we have to get used to floating point math weirdness. So we get a big number, not quite infinity, but big number. And then this is negative 1, and then again, something not quite 0, but small number, 10 to the minus 16. So anytime you see like 10 to the plus 16, 10 to the minus 16, you know, it's just an artifact of floating point precision, you know, weirdness, where you can't quite get it to 0, but you're getting something close to 0, or you're not, you know. And then again, when you try to take the tangent of something approaching, you know, where, you know, one of the dividing by something that's approaching 0, you know, then the result approaches infinity, but again, you're not going to get infinity. Okay, log and the exponential function. So you have, anytime you see dot log, that's going to be natural log, ln, and then dot log 10 will be common log. I wish this is how we taught log in high school, but in high school we always write ln and then log, and then when you translate it over into computers, then you had to say log and log 10. But I just wish we would just say log is all like base e, but whatever. Okay. All right, so you have 0, 10, 100, and so when you do common log long 10, you get 0, 1, and 2. That's exactly what we'd expect. All right. If you do, you know, e raised to this, so e to the 0, e to the 1, e to e squared, okay? You have exp2, this is 2 raised to the y, okay? So you're going to get 1, 2, 4. And then you also have the dot power function, okay, numpy dot power. You put in whatever number you want. So 3 raised to 0, 1, 2 gives us 1, 3, and 9. Okay. Oh, careful. Okay, we have the numpy.sum, okay? If you have a big array and you want to add them up, do numpy.sum. Don't do regular sum, okay? Because again, numpy.sum has been optimized to work with numpy arrays, and it's going to be way faster, okay? And I think I've got some demonstrations of this. So here I'm going to create an array 0 through 99, okay? And then you say, hey, I want to add these up, okay? And it does it really fast, right? I mean, we have the, what, n times n plus 1 divided by 2 or whatever. That's like the formula for adding up a bunch of integers and stuff. You know, same thing, but you know, it's actually adding them up, and you get, you know, 4950. Numpy.sum, oh, sorry. So this is sum, and numpy.sum, you get the same result, okay? But the numpy.sum is just much more efficient. So use numpy.sum rather than plain old sum, okay? And this is, oh, and I didn't, did I run this? Let me see. I didn't run this. Okay, there is a, if you uncomment the %time it, this will take a few seconds to run, okay? But it's, because it's doing this thing where it repeats the thing. And you could see when I had an array of 10,000 random numbers, okay, the sum took 624, what is that? Microseconds, plus or minus 14 microseconds, something like that, I don't know, okay, versus the numpy.sum took 5.84 microseconds. So plus or minus 354 nanoseconds, I think. So anyway, the NumPy sum is like 100 times faster, right? It's like 1/100th the speed, so or the amount of time it took. So always do NumPy.sum. Okay. You also have min and max. Okay. So you could search for the minimum value of a big array, the maximum value of a big array. So when you did 10,000 random uniform numbers, the largest value we got was 0.99994. And the smallest value we got was 0.00012. Okay, NumPy.min and NumPy.max also same thing. And again, these things, it'll take a few seconds to run to do the % time it because it's running a whole bunch of these loops. But again, the NumPy.min and the NumPy.max is going to be much faster than the regular min and max function. Okay, again, something like searching for the minimum value or searching for the maximum value within an array is going to be optimized for NumPy. Okay, sometimes we want to just calculate summary values, like you want to calculate the sum, okay? Now the regular sum function is kind of weird in that, like, if you have this two-dimensional array, 3 rows, 4 columns, and you call sum on this matrix here, it's going to give you a vector of 4 values, okay? The column sums, which is, in my opinion, a weird thing. Okay, NumPy.sum, I think, behaves a little bit more like what you would expect, and it's just going to take all of the 12 numbers and then sum them up, and it gives you 66, okay? Okay, you can call NumPy.sum and specify an axis. So you could say, I want to sum along axis 0, okay? So what this means is, remember, axis 0 is the rows, axis 1 is the columns. So when you say axis 0, you're summing over the axis 0, okay? So basically, if you think about the shape of this thing, which is 3 by 4, okay? When you do axis 0, it's going to collapse that the shape for the 3, right? It's 3 by 4. It's going to collapse the index 0. So it's going to collapse the 3 down into one row, and we get the values, right? Axis 1 is going to take the 3 by 4, and it's going to collapse that 4 down to a 1. So we're going to get 3 rows, or the sum across the rows, basically. Okay, so we get 3 values. Okay, same thing, you can search for the min across axis 0 or the max. You can do standard deviation of the whole thing, standard deviation across the rows, standard deviation across the columns, and so you have all of those things. Here, if you have a higher dimensional array, same kind of thing, okay? All right, so here's a quiz. I have matrix A. It is 2 by 3 by 4. Everything in here is a 1, okay? If I say axis equals 0, okay? So remember that the shape is 2 by 3 by 4. What is the resulting shape of np.sum axis 0 going to be? Two by 3 by 4. We are collapsing axis 0. So we're going to collapse axis 0, which is the 2. So the result is going to be a 3 by 4. Okay? And so we're going to get a 3 by 4 thing, and everything, when we do that, everything's going to be a 2 in there, right? So we're going to get a 3 by 4. Okay? What if I collapse axis 1, what is the result going to be? Huh? 2 by 4, right? It's going to be a 2 by 4 because we're collapsing. So remember, it's 2 by 3 by 4, so axis 1 corresponds to the 3. We're collapsing that 3, and we're going to get resulting a 2 by 4. Okay, does that kind of make sense? So we're basically adding up there. And then if I collapse axis 2, okay, we're going to get a 2 by 3. Okay, and everything adds up to 4, right? So that's how it works in higher dimensions. In terms of doing some kind of sum. And obviously, you can replace .sum with .standard deviation, .min, .max, any of those types of things, okay? All right, we have, if you have a missing value in in NumPy, we call this, we designate it with nan, okay? So nan is for not a number, okay? And we can do, we'll do float parentheses, or float quote nan, okay? Float nan, and that's going to create a nan type, okay? You also have float infinity, and if you do things like infinity divided by infinity or infinity minus infinity, these result in non-existing numbers, okay? You know, so anyway, that's what we have. Okay, so if you try to do like 7 minus infinity, you'll get negative infinity. If you do like a finite number divided by infinity, it'll just say 0, okay? But if you try to do a sum, so remember x is nan, okay? If you try to say sum a nan with a 2, the result is a nan, okay? Okay. However, if you have a vector or an array where you have missing values, okay, you can do something called nan sum. Nan sum basically ignores anything that's a nan, okay, and it sums everything else. So in this case, nan sum will just be 2, right? And same thing with mean. Nan mean, I've got, every time you see an x, that's a nan value. So it's going to just take the mean of the values that aren't missing. So it's going to just take the mean of 2 and 3, and it'll return 2.5. Okay, 2.5. And so these are all of the different kind of sorry. These are all of the different kind of summary functions. So things like sum, product, mean, standard deviation, variance, min, max, argmin, argmax, median, things like that. And you have the nan versions, which will just ignore anytime you have a nan. Okay. Otherwise, if you don't use the nan version and you do have a nan, it will return a nan. Okay. Oh, I have forgotten about view quiz answers. Okay, let me go ahead and give you the first two. The first two answers are A as in apple and E as in elephant. A as in apple, E as in elephant. A and E. Your first two answers. Okay, so those are the NAND-safe versions. Okay, Python does something called broadcasting. Okay, broadcasting is kind of like recycling values in R, but it only works when dimensions are compatible. So anyway, I have this one-dimensional array A with the values 1, 2, 3. B has values 4, 5, 6. I say, hey, add A and B together. It adds them element-wise, 1 and the 4, 2 and the 5, 3 and the 6, and we get 5, 7, 9. Okay, now here I have another vector, or another array with the values 7 and 8. Now, if I try to add A and C together, it says I don't like that, right? Because A is 1, 2, 3, and C is 7 and 8. So it says these things don't align. You have length 3 and length 2. I don't know how to do this. Okay, so it gets upset. Okay. Here I've got A, which is 1, 2, 3. And then I'm going to create E is a 3 by 3 just full of ones. Okay. Here I can add E and A. All right. So again, E is a 3 by 3. A is 1, 2, 3. And so what this is going to do, Python or NumPy does what it says is broadcasting. It's going to take this length 3, and it's going to look at this thing E, which is 3 by 3, and it's going to basically kind of like it broadcasts that length 3 thing into a 3 by 3 matrix itself, okay? And so this basically the 1, 2, 3 gets repeated, okay? And so it adds it across the first row, the second row, and the third row. Okay. If I reshape A into a vertical column, 1, 2, 3, down the column here, and I say add E and A together, again, E is this 3 by 3 thing, it's going to broadcast the column, and it's going to add 1, 2, 3, 1, 2, 3, 1, 2, 3 down the column. So we'll get the first row will all be 2s, the second row will all be 3s, and the third row will all be 4s. Okay. Okay. So here is another matrix D, which is a 2 by 3. A is a length 3, and if you do D plus A, it's going to broadcast A across the rows. Okay, so it adds 1, 2, 3 across the top and 1, 2, 3 across the bottom. Here, C is 7 in this two-dimensional thing. Okay, and D is length. C is a length 2 thing. It's a one-dimensional length 2, and D is two-dimensional 2 by 3. Okay, and here it's if I try to do D plus C, it says I don't like that. Okay, I don't like that. Okay, but if you reshape C to be a column, 2 rows, 1 column, then it will broadcast, right? So it will add 7 across the top row and 8 across the second row. Okay, but it required us to take D and then we reshape it into a column that's 2 by 1, and then it will repeat it across the whole thing. This is where broadcasting gets so I think this makes sense, right? Like taking the length 3 and then basically it treats it like a row vector and it adds it across the rows. And then here I got the length 2, and then if I have to convert it into a column, and then it can add it across the other thing. Okay, this is where broadcasting gets a little bit weird. You can also broadcast to basically a column, like a column matrix and a row matrix, or actually this is just a row vector. But E is 10 by 1, and F is just length 11. Okay, but NumPy often treats one-dimensional things when you do broadcasting as if it were one row. Okay, like it'll treat it kind of like a 1 by 11 thing. Okay, so if I say E plus F, okay, NumPy looks at this and it says, okay, this is 10 rows, 1 column, and it's going to look at this and it's going to say, okay, we're going to treat this like it's 1 row, 11 columns. Okay, so I got a 10 by 1 and a 1 by 11, and then it's going to broadcast both of them simultaneously into a 10 by 11. Okay, so it's going to broadcast the E, basically replicate it across 11 columns, and then it's going to take this thing, which it's going to treat like a row vector, 1 row, 11 columns, and then it's going to duplicate across like 10 rows. Okay, so what you end up getting is you end up getting a 10 by 11. Okay, a 10 by 11 where it just took the entire column, added them across, and then took the entire row and then added it across. Okay, you can do E star F. Okay, and again you get it gets broadcast and then it gets multiplied element wise. Okay, and this is basically like your times table that you had to create in, I don't know, 3rd grade or something. Okay, so 1 times 1, 2 times 2 times 2, 2 times 3, 2 times 4, so on and so forth. Filling it out that way. Okay. All right. If you do something like, you could even, this is just kind of like even weird stuff that you can do. You can reshape D into a 1 by 6 and D into a 6 by 1. And then you add them together, and then they get broadcast into basically a 6 by 6 thing. Okay, so just kind of like, oddities that can result from these broadcasting. Okay, so this is probably the weirdest behavior of the broadcasting that maybe takes a little bit of extra thought to kind of work through there. Okay, we have a bunch of Boolean operators. So basically, if you do a comparison, you'll get a true false. Okay, so here I have X is just 0, 1, 2, 3, 4, 5, and you can just do, hey, is it less than 3? And you'll get true, 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 false, false, false. Okay, greater than or equal to 3 is going to be the complement of that. Okay, is it equal 3? Okay, and then once you have basically an array of true and false values, you can subset. Okay, so you could say X subset to those Boolean values. Okay, so when you say subset X such that it's where x is greater than or equal to 3, we're going to just get those values 3, 4, and 5. Okay. You could say, hey, sum the Boolean thing. Okay. Basically, the falses get turned into zeros and the trues get turned into ones. Okay. So this will basically be the count of how many things where this is true. So you get the integer 3. Okay. If you say, hey, the mean, okay, now you're taking the mean of zeros and ones, and you'll get the proportion of things that are true. Okay, so you get the float 0.5. Okay, this tilde operator is the not sign. Okay, so you it turns trues into falses and falses into trues. Okay, so this is print where it is not, x is not equal to 3. Okay, now you have to be careful. Okay, tilde x. Okay, tilde. So, oh, I have it. Okay, so this just gets weird. Okay, if you do tilde x equals 3. Okay, this is here. X is 0, 1, 2, 3, 4, 5, and if you do tilde x, okay, tilde x. Is like a not sign, but it just turns everything into negatives, which is, it's like, what? Okay, because basically when you, if you take the trues and the falses, then you call tilde on it, it kind of like inverts them. So it's kind of like, it's like putting a negative sign on true false values, but this is the operator that we use. You don't actually want to use a negative sign when you're doing true false values. So you use the tilde operator, okay? But if you use the tilde operator on things like integers, it acts kind of like a negative sign. So, but that's bad habit, okay? You should use the tilde sign only for Boolean things, and then use the negative sign for numeric things, okay? But if you mix them up, then you start kind of getting these like funny behaviors. But so just kind of be careful. Same thing with matrices. You can get Boolean things in there, so you can get a matrix of true and false values. All of these things, you do the sums and the you can means, and you can sum across axes and things like that. Okay. You have if you've got arrays of Boolean values. Okay. Now we have the and the or operator, okay? Now, these are different. These are bitwise Boolean or element-wise Boolean operators versus, so Python has the word and for and the word or, okay? And we use those things like in if statements, conditional statements. When you have a loop, all right, you do, condition 1 or condition 2 or something like that. Okay, and you spell out the word or. You don't use the and or the or operator here. These and or operators are vectorized, and they are designed for NumPy arrays where you want to do first element compared with the first element, second element compared with the second element. Okay, so these are different use cases. Okay, so we have the vector true, false, false for A, and then true, false for B, and then the and, both of the things have to be true. You have the or operator, which is the vertical line, and one of those things, okay? And then you have the this caret operator is the exclusive or, so one must be true and one must be false for it to be true, okay? So if it's true, it results in false. The true, false, and the false, true becomes true, and then the false, false remains false, okay? And then the tilde is the bitwise not, so it flips everything around. And then you have any and all. Any is, are any of the things in that array true, versus dot all is, are all of the values in that array true, is what you get, okay? NumPy things support what's called fancy indexing, okay? And what this means is basically you can pull out like elements that correspond to certain indices, okay? So here, X is this array, okay, with these values 37, 12, 72, 9, 75, so on and so forth. Okay, and here I could say I want to extract elements at index 0, index 1, and index 5. So we're going to get out 37, the 12, 0, 1, 2, 3, 4, 5, and the 5. Okay, so we'll get the 37, the 12, and the 5. So we'll get the values corresponding to those index positions, 0, 1, and 5. And that's what NumPy calls fancy indexing, where you're pulling out some of these things at these odd indices. Okay, here I have an array. Okay, a 2 by 3 array with values 1, 2, 3, 4, 7, 8. I'm sorry, 1, 4, 7, 2, 3, 8. Okay, and if I say I want to pull out elements 0, 1, and 5. Okay. Wait a second. Print X. Oh, okay. Sorry. Now, sorry. So this is not. We are subsetting. Okay. Sorry. This is a little bit of a weird thing. Not 0, 1, and 5. Okay. We're subsetting X based on these indices. Okay. So remember, X is this vector 37, 12, 72, 9, 75. And then we're saying get index 1, okay, put is 12, that goes in the top left corner. Okay, the next value here is 4, index 4, which is 75. The next value is index 7, so 64 goes there, so on and so forth, and it fills out the matrix according to the indices in this index array here. All right, here is another matrix, X, 0, 1, 2, 3, 4, 5, 6, 7, up through 11, okay? And here I can say pull out the values in X that correspond to these things. So we're going to go row 0, column 2, so we're going to get out the 2. Then we say row 1, column 1, so we get out the 5, and then row 2, column 3, and we get the 11, okay? So we're going to say subset X based on the row and the column, and we're providing these things, and you can kind of extract out those elements. All right, you can take an array and you can call shuffle. So NumPy has its own, has these, again, random operators, right? So we looked at like random number generation, but you also have things like you can take something and just shuffle them. So we have, 0 through 5 getting shuffled around. Dot sort will sort it in place, and so you'll get exactly what you expect, 0, 1, 2, 3, 4, right? You can call argsort, okay? Argsort will tell you if you wanted to sort these, what is the index of the thing that you want to put in order, okay? So the original array is 5, 2, 1, 4. So if we wanted to sort them, okay, then we would get index element 2, which is the 1, then index element 1, which is the 2, then index element 3, which is the 4, and then index element 0, which is the 5. Okay, so if I say D is 2, 1, 3, 0, and then I subset Y based on D, then it will be in the order 1, 2, 4, 5. Okay, you can also, when you call sort, you can sort along certain axes. So you can say sort along axis 0, and it will sort down the columns. Okay, we could say sort along axis 1, and it sorts across the rows. So each row is now sorted, and you have all of that. Okay, subsetting and slicing. So I could say I want row 0, and you can also do .argsort. So here I could say take column 1, and then do a .argsort, and then you can sort based on that one particular column, resort the entire array. Okay. So these are just different kinds of things that you can do with NumPy as far as sorting. Argsort is kind of like you have to think when you use it. It can be helpful and it can be handy, as far as dealing with arrays here. All right, let me go ahead and I will give you the final ViewQuiz answer. and that will just be for those in person. So